The solar system is usually shown as a flat disk. 8 planets, circling the sun on a neat, tidy plane. It makes for clean diagrams, easy to visualize, easy to teach. But it raises a question most people never think to ask. What is above that disk? What is below it? Is it empty? Is it a void? Or is there something out there, waiting to be understood? The answer is more interesting than you might expect, because once you leave the familiar plane of the planets, you enter regions that are vast, mysterious, and largely invisible. Structures that surround us in every direction. Structures that connect us to the larger galaxy. Structures shaped by events that happened millions of years ago. Before we look above and below, we must understand why the planets orbit in a disk at all. 4.6 billion years ago, long before Earth existed, long before the sun ignited, there was only a cloud. A vast cloud of gas and dust drifting through the galaxy until something disturbed it. Perhaps a nearby supernova, perhaps a passing star. The cloud began to collapse under its own gravity, and as it collapsed, it began to spin. And as it spun, it flattened, the same way pizza dough flattens when you spin it. Physics demanded it. The result was a rotating disk of material surrounding the young sun. Planets formed within that disk, coalescing from dust and gas, growing larger over millions of years, which is why they all orbit in roughly the same plane today. We call this plane the ecliptic. Not everything is perfectly aligned. Mercury is tilted about 7 degrees. Pluto is tilted nearly 17 degrees. Some comets come in at almost perpendicular angles, like needles piercing a vinyl record, remnants of a more chaotic past. But the main planets, Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, all within a few degrees of the same flat plane, a disk inherited from the cloud that made them. Here is something most diagrams do not show you, something that changes everything. The plane of the solar system is tilted 60 degrees relative to the plane of the Milky Way galaxy. Think about what that means. The galaxy is often pictured as a flat disk of stars, with spiral arms stretching outward, and a central bulge of ancient stars. Our solar system sits within that disk, about 26,000 light years from the center. But we are not aligned with it. We are tilted sideways, like a coin leaning on a table. So when we talk about what is above and below the solar system, we are really talking about directions that point partly ahead and partly behind us as we orbit the galactic center. The sun travels around the Milky Way at approximately 515,000 miles per hour, a cosmic journey that takes 225 to 250 million years to complete, one galactic year. But because of that 60-degree tilt, our motion through the galaxy is not perfectly horizontal. We are cutting through it at an angle, rising and falling relative to the galactic plane, like a horse on a carousel. On Earth, we know what up and down mean. Gravity pulls us toward the ground. The sky is above. The floor is below. We learned this before we learned to walk. In space, that logic disappears. There is no fixed floor, no universal ceiling, no up, no down, only relative positions. An astronaut floating in orbit might be upside down compared to another astronaut, but neither of them is wrong. There is no right way to orient yourself when there is no gravity to guide you. So when astronomers talk about what is above or below the solar system, they use the ecliptic plane as a reference, the flat disk where the planets orbit. It is an arbitrary choice, a human convention, but it is useful for mapping what surrounds us. Using that framework, we can begin to explore. The first major structure we encounter is not above or below. It is all around. The Oort cloud, a theoretical shell of icy objects that completely surrounds the solar system in every direction, above, below, and everywhere in between. Unlike the flat disk of planetary orbits, the Oort cloud is spherical, a vast bubble of frozen debris, encasing our solar system like a shell around an egg. It extends from roughly 2,000 AU to as far as 100,000 AU from the Sun. For reference, Neptune orbits at about 30 AU. The Oort cloud's outer edge is nearly a quarter of the way to Proxima Centauri, the nearest star. This cloud is made of trillions of small frozen bodies, mostly water ice, ammonia, methane, leftover building blocks from the formation of the solar system, debris that never became planets. Early in the solar system's history, gravitational interactions with Jupiter and Saturn flung these icy chunks outward. Some escaped entirely, lost to the galaxy forever. Others got trapped in enormous orbits, taking millions of years to complete a single loop around the Sun. These trapped remnants now make up the Oort cloud. We have never directly observed the Oort cloud. It is too far away, too faint. The objects within it are too small and too dark to see. But we know it exists because of long-period comets. These comets take thousands or millions of years to complete one orbit, and they come from all directions, not just the flat plane of the planets, from above, from below, from angles no planet has ever traveled. That spherical distribution is the signature of the Oort cloud, invisible, but undeniably there. Closer to home, there is another structure that surrounds us, in every direction, including above and below the ecliptic. The Sun constantly releases a stream of charged particles, called the solar wind. Protons, electrons, helium nuclei, racing outward at hundreds of miles per second. As these particles travel outward, they push against the particles from interstellar space, the gas and dust between the stars, creating a kind of protective bubble around the entire solar system. This bubble is called the heliosphere. The heliosphere is not perfectly round. It is more like a distorted teardrop, compressed on the front side, stretched out behind, because the solar system is moving through the galaxy. Think of a boat moving through water. A wave forms at the bow. A wake trails behind. The heliosphere works the same way, shaped by motion, shaped by collision. The boundary where the solar wind finally slows down and begins interacting with interstellar material is called the heliopause, the edge of our bubble, the border between us and them. Beyond that lies interstellar space, the vast, cold region between stars, where the Sun's influence ends and the galaxy's influence begins. Voyager 1 crossed the heliopause in 2012. Voyager 2 followed in 2018. They are now traveling through interstellar space, the first human-made objects to leave our bubble, but still technically within the outer reaches of the Oort cloud. Even in interstellar space, we are not floating in a complete void. The Sun is currently passing through a region called the local interstellar cloud, a patch of slightly denser gas and dust within the broader interstellar medium. It is not much denser, still far emptier than any vacuum we can create on Earth, but denser than the surrounding space, enough to matter. As the Sun moves through the galaxy, it encounters different regions, some denser, some more sparse. The local interstellar cloud is just one stop along a journey that has been going on for billions of years and will continue for billions more. This cloud extends above and below the ecliptic plane. It is not flat. It surrounds us in 3 dimensions, providing the raw material that the heliosphere pushes against, the resistance that shapes our bubble. Zoom out further, and we find something remarkable. The solar system sits inside a vast region of space, called the local bubble, a cavity approximately 1,000 light-years across, where the density of matter is unusually low. It is like a cosmic void, not empty, but far less dense than the surrounding regions of the galaxy, a bubble within the galactic medium. How did this bubble form? Supernovae. Astronomers estimate that at least 15 supernovae exploded in this region over the past 14 million years. These massive stellar explosions pushed gas and dust outward with tremendous force, carving out the cavity we now occupy, clearing a space in the cosmic fog. The solar system was not always inside this bubble. About 5 million years ago, our path through the galaxy carried us into the local bubble. We entered through its outer wall, a denser region of gas and dust piled up at the edge, like snow pushed aside by a plow. We have physical evidence of this journey. Deep-sea sediments on Earth contain elevated levels of iron-60, a radioactive isotope that can only form in supernovae. The timing of these deposits matches when we would have crossed through the bubble shell, evidence of a cosmic journey preserved in ocean mud. The local bubble has walls, denser regions at its edges where material has accumulated. Inside, we are surrounded by a cosmic cavity. And on those walls, new stars are forming, triggered by the compression from ancient explosions. It is like our solar system is floating inside a giant room, surrounded by cosmic walls, shaped by stellar deaths, that happened millions of years before humans existed, before mammals dominated the Earth, before dinosaurs went extinct. Zoom out even further, far above and below, not just the solar system, but the entire disk of the Milky Way, and we find the galactic halo. The Milky Way is not just a flat disk of stars. Surrounding that disk is a roughly spherical region, extending far above and below the main galactic plane. This halo contains older stars, globular clusters, and possibly large amounts of dark matter, the mysterious substance that holds galaxies together. The halo is where some of the oldest objects in the galaxy reside, stars that formed when the universe was young, before the disk structure fully developed, before spiral arms existed, witnesses to a younger cosmos. This reminds us that up and down are only meaningful when we agree on a reference. Relative to the ecliptic, we can't talk about what is above the solar system. Relative to the galactic plane, we can't talk about what is above the Milky Way itself. At every scale, there is structure, there is motion, there is history, written in the positions of stars and dust. When we look at textbook images of the solar system, we see a neat, flat arrangement of planets. It is useful for teaching orbital mechanics, but it gives the wrong impression. The reality is far more complex and far more interesting. Above and below the plane of the planets, we are surrounded by icy debris from the solar system's formation. We are enclosed by a bubble of solar wind pushing against interstellar gas. We are passing through clouds of material between the stars. We are floating inside a vast cavity carved by ancient supernovae. We are wrapped in a halo of dark matter and ancient stars. The solar system is not isolated. It is connected to the galaxy at every level, moving through it, shaped by it, carrying evidence of cosmic events in the very rocks beneath our feet. And perhaps the most remarkable thing is this. Despite all that complexity, the spherical shells, the cosmic bubbles, the supernova debris, the dark matter halos, the violent explosions, the endless drift through space, life emerged on a small rocky planet near an ordinary star, inside a cosmic cavity created by stellar deaths. We are not just observers of this structure. We are part of it, made from it, connected to it, forever. We mentioned Voyager 1 crossing into interstellar space, but its journey is far from over. The spacecraft is still traveling, still pushing deeper into the unknown. But how far will it actually go before it finally stops forever? Watch how far will Voyager 1 actually travel before it stops forever to find out.